delving into discrete normalizing flows on SO3 manifold for probabilistic rotation modeling. Normalizing flows is a powerful tool to construct complex distribution by a sequence of invertible transformations of a base distribution. Rotation, as an important quantity in computer vision and robotics, can exhibit ambiguity and thus demands probabilistic models. Though much progress has been made for flows in Euclidean space, there are no effective flows without discontinuity or many-to-one mapping tailored for SO3 manifold. Given the unique properties of rotation, adapting the existing flows to SO3 manifold is non-trivial. In this paper, we propose a novel normalizing flow on SO3 by combining a Mobius transformation-based coupling layer and a quaternion affine transformation. Extensive experiments show that our rotation normalizing flows significantly outperform all baselines on both unconditional distribution fitting and conditional pose estimation tasks. Detecting object rotation from a single image is a very important task in both vision and robotics. It can be used in augmented reality, robotic manipulation and many other regions. Along with rotation regression predictions, endowing a neural network with the ability to express uncertainty is very crucial to safety. The extra information tells us how well we can trust the result, which is very important in interpretability critical systems and can be used for some downstream reasoning. In recent years, there has been much effort in modeling the uncertainty of rotation via probabilistic modeling of SO3 space. It includes von Mises distribution for Euler angles, Bingham distribution for quaternions, matrix Fisher distribution for rotation matrices, and etc. However, these distributions are all single-modal and cannot express arbitrary flexible distributions. In real world, there are many symmetric objects with multiple or sometimes infinite correct poses. The box and vase are very ubiquitous and they possess either a 24-modal distribution or a continuous distribution. One-modal distribution like matrix Fisher distribution is clearly not sufficient to model such distributions, and here comes the problem of how to model an arbitrary distribution on SO3 manifold. Thus we considered normalizing flows. To construct complex density over a high-dimensional vector X, we can first sample from a base distribution, which is usually easy to calculate and sample, and transform this sample through an invertible and continuous transformation. The probability distribution is thus transformed according to the change of variable formula. Though there have been many efforts made in flows in Euclidean space, flows for SO3 manifold are still underexplored. Previous discrete normalizing flows are not directly built on SO3 manifold. Rayleigh construct flows on Lie groups, and the axis angle representation for SO3 is a special case of Lie group. It uses log map or exponential map to transform between SO3 and its Lie algebra, and applies flows in Lie algebra space. Rayleigh suffers from discontinuity and fails to model highly concentrated distributions. Pro-HMR uses 6D rotation matrix representation and applies flows on 6D vector space. The transformed 6D vector is projected to 6D rotation matrix by Gram-Schmidt orthogonalization. While the projection process is a many-to-one mapping, it is not a normalizing flow and can't calculate probability distribution function. On the other hand, continuous normalizing flows, or CNF, can also be adapted to the SO3 manifold. RCNF directly adapted CNF onto Riemannian manifolds. However, as the learned trajectory can be very complex, it would be harder to train and time-consuming. Moser flow improves it by constraining the flow to be within a specified type, but it models the probability as the probability of base distribution minus the divergence of a neural network, which is not log scale and is thus suboptimal when the probability is too low or too high. Our method uses discrete normalizing flows, by stacking multiple building blocks, directly transform elements on SO3 manifold. Each building block consists of Mobius transformation-based coupling layers defined on rotation matrix and an affine transformation defined on quaternion representation, connected by conversion between rotation matrix and quaternion. We use negative log likelihood of ground truth rotation as supervision and evaluate by either computing log likelihood or accuracy. Mobius coupling layer utilizes the idea of coupling layers in Euclidean space. Divide the variables into two parts, with one fixed and the other transform conditioned on the fixed parts. We use similar ideas. Rotation matrix can be regarded as three orthogonal unit vectors, therefore can be divided into two parts. With one column fixed, the next two columns are restrained into a plane vertical to the fixed column, lying on a circle. We can therefore use transformation on a circle to transform the second column, and the third column can be calculated via cross product of the first two columns. For transformation on a circle, we choose Mobius transformation. Mobius transformation has a very straightforward geometry, meaning it's the minus of the intersection point of the line of parameters omega and point C with the sphere. As transformation on the circle only has one degree of freedom, we can parameterize the output as an angle, and use weighted sum of angles to further increase its expressivity. To avoid discontinuity in such naive construction, we also provide a square root of 2 divided by 2 trick. We also create a quaternion affine transformation. To satisfy the geometry of SO3 manifold, we apply an invertible 4x4 matrix on the quaternion and project it into the unit sphere. Via SVD decomposition, the transformation can be decomposition into 3 operations: rotation followed by scaling and normalization, and followed by rotation. These 2 operations make up what is hard for Mobius transformation to do. As rotation operation in rotation manifold is an analogy to replacement in Euclidean, the function of quaternion affine transformation is very similar to affine transformation in Euclidean space, and that's what it is named for. We conduct experiments on fitting various challenging distributions on SO3 manifold, and in all experiments, our method can capture the distribution well, and our results surpass all baselines. Our normalizing flows can be easily extended to a conditional version, with parameters or base distribution conditioned. Therefore, we can compare our results on pose estimation task. We compare our methods on SimSol 2 dataset. SimSol 1 contains images rendered around simple symmetric solids. The symmetry of geometric objects are broken with some small markers in SimSol 2 datasets. We also evaluate our algorithms on common benchmark datasets ModelNet 10 SO3 and Pascal 3D+. On SimSol 1 datasets, our methods can accurately capture the symmetry of geometric objects, and as well can recognize the symmetry breaking in SimSol 2 datasets due to the markers on geometric objects. The experiments on ModelNet 10 SO3 datasets further proves our method's effectiveness and robustness to Model 1 modal distributions. We also achieve state-of-the-art performance on pose estimation of Pascal 3D+ dataset. Ablation study shows the effect of the 2 parts of our models. Mobius coupling layers are the base of our models, and quaternion affine transformation can quickly concentrate distribution and accelerate learning speed. In conclusion, we propose the first time a discrete normalizing flows for SO3 manifold without singularity. It achieves superior performance over all baselines on both fitting the target distribution on SO3 or estimate pose give input image. Thanks for your listening.